In this video, I wanted to talk about what are the issues with rounded quotas and why can't we just use those? So let's return back to the parking space problem and let's just actually start doing an apportionment problem. So basically, in the last video, I was trying to set up the idea and all of the important need to know terms and everything. Now let's actually get into the math. So for that example, let's say we were actually going to apportion each of the parking spaces to the different groups. What it all starts with is the standard divisor, as I was saying, but basically what I suggest doing is to make a table with all the numbers and information in it. So in this problem, we had 77 faculty members, 174 staff members. And then we had 295, 240, and 150. Let me just double check, make sure I got all those right. Not that it really matters if I mess this up because this is just an example anyways, but cool. So basically we have a number of people, basically the individual populations of each of our different states. And then basically the total was also important, which was 936. And step one is to always find, well, what's the sum of all of your populations and divide it by the number of objects to be apportioned. And remember, capital M is for the formula for the standard divisor, it's always P over M. It's not P over N. N is the number of groups. M is the number of objects. Which is, in that problem, we had 100 parking spaces. So it's always how many people do I have and how many objects am I trying to give to them? And that's what you're dividing. But basically, step one is to take each individual population and divide by the standard divisor. So if we have a layout such as this, what I can kind of remember is I want to divide each one of those to find the standard quota. So we've already done this for the faculty members, but their standard quota was approximately 8.23. And obviously the exact standard quota is technically the exact value of the fraction. Not like this is an approximated value because I'm rounding it a little bit, but it for our purposes and for most purposes in general, it's good enough to just round it off by, say 3 or 4 significant figures. But in the case of the staff, their standard quota would be approximately 18.58. When it comes to upperclassmen, 295 divided by 9.36 would be 31.52. And yeah, I should have rounded the staff differently if I was rounding to the nearest hundredth, but it doesn't usually matter that much, and we'll get into why when it does matter and when it doesn't matter. But in this example, it really doesn't matter, which is why I'm not being very careful. But sometimes you do need to be careful in very specific methods, but we will get to that. So anyways, let me go ahead and finish calculating all of the standard quotas. But doing so, basically what these numbers are telling us is what is the proper division of the seats to the states. And basically, in this case, each state should get that many seats, or in the term of the problem, each of those groups should have that many parking spaces. And of course, the issue is we can't give this many parking spaces to those groups. So what we can do is, well, what if we were to round them conventionally? So this would 8.2 would round down, 18.5 would round up, 31.5 would round up, 25.6 would round up, and 16.03 would round down. And so you might say, well, let's just give each of those groups this many parking spaces. Cool. Done. Issue's over, right? But one of the issues with using the rounded quota is actually if we go back and add these numbers up, 8 plus 19 plus 32 plus 26 plus 16, notice that, well, there's 4 even numbers and 1 odd number. That's not going to add up to an even number of objects. And actually what that will end up adding back up to is 101. And notice that you don't actually need to find the sum of the standard quotas because that should actually add up to exactly 100 in every case, which is why I didn't bother to do that. But it's not that I'm just going to put an X there because it's something we don't care about. But in this case, using the rounded quota, here's the issue, is that if we just do a perfect division of all the objects, we're going to almost always get a bunch of decimal numbers. If we just round them off normally, it doesn't actually add back up to what we're trying to do. Our goal was to distribute 100 parking spaces to each of those groups, but what we actually did in this is give out 101. And you might be saying, well, what's the big deal? It's one off. Who cares? But in a lot of cases, like when a university actually has 100 parking spaces, you can't necessarily just give out one extra because it doesn't have that space. So if we're giving out 101 spaces, this is not a proper solution to the problem. And so this method is not an apportionment method. But like this example shows us how does apportionment work, but basically an actual method is a little bit more complicated than just this. And that's, what we're going to get into in the next few videos, what are different methods of apportionment, and, how do those affect the outcome. But at the same time, sometimes we might be asking to find, well, what's the upper quota and what's the lower quota? In each of those cases, that just means upper quota, take the standard quota round up regardless. So if we were talking about, well, what would be the upper quota for the faculty, we would just take 8.23 rounded up. Basically go to the next number, and all of those would be rounded up regardless of the decimal behind them. Even if it's 16.03, right? It doesn't matter how close it is to 16, it's going to be rounded up. And also, just as a thing to mention, if your standard quota does come out exactly round, you don't need to round it. You don't need, like, the upper quota doesn't mean add 1 to it. It just means if it's round, it's round. You don't ever need to round it again, because that means you can give exactly the amount that you should, as what the standard quota indicates. And the lower quota would just be rounding down regardless of what the numbers would be. So like in each of those cases, the upperclassmen should have been 26 for the upper quota. Now that I'm looking more carefully at it, that's really, really horrible. That's not that much better. But anyways, basically the upper quota would be the sum of all of the, round them all up, and the lower quota would be add up all of the standard quotas rounded down. And also another problem with those quotas is that, as you could expect, well, if we round them all down, we're going to come up short, right? 8 plus 18 plus 31 plus 25 plus 16 would give us only 98 parking spaces. So that answers a little bit better, because we actually could give out 98 spaces, but we would be, we'd still have 2 left over. So what do we do with those parking spaces? And that's exactly what Alexander Hamilton figured out, and he invented his own method for doing this for the U.S. House of Representatives, if I recall correctly. And that's the first method we're going to be talking about in 4.2, is called Hamilton's method of apportionment. And he started with the lower quota and basically gave out what we call the surplus. In this case, we would refer to the surplus as having 2 extra seats left over. And if we do all the upper quotas, the obvious issue is, well, we're going to be giving out too many seats. That would add up to 103. And so notice that no matter how I'm rounding it here, there's always an issue, and it doesn't necessarily work. Now, sometimes the rounding quota might actually be a proper apportionment method, but not typically. It's not incredibly likely for it to work. And this is the key conundrum with apportionment. How do we go from here?